Welcome back. We spent the better part of this semester talking about Python, data structures, algorithms, classes, object-oriented programming. And if you'll recall, one of the themes in all of this is the power of abstraction, the power of compartmentalizing either data or code so that the nitty-gritty details of it don't have to be part of our work in writing code around that. And there's a really powerful notion of abstraction. And in the last part of this course, I want to talk in some ways about the ultimate abstraction, which is a computer. We use these things routinely, whether they're handheld devices, laptops, or desktops. And they're remarkable. They do incredible computations. And do we know exactly how it works? Well, for the most part, no. It's an abstraction. We know that when we turn on the computer and save a file, something happens. We know when we turn on a computer and ask the computer to add two numbers or divide two numbers, it just sort of works. But how? How is that nature of that computation working? And because I think it's important to understand this very tool that we are using on a daily basis, we're going to spend the last part of this class talking about that abstraction, which is how do modern day computers work. Now, obviously, this can't go into every little bitty nitty-gritty detail of how a modern day computer works, but I'm going to show you the building blocks of a modern day computer. And what is, I think, really truly remarkable about that is how incredibly simple they are. Okay, so let's go ahead and dive in first and see how computers actually work. All right, so let me first start talking about the language of modern day computers, which are binary numbers. But before I do that, let me talk about the numbers that we all know and love, which are base 10 numbers. Okay, and then we'll talk a little bit about binary numbers. So when I say the number 723, you and I have a common language. What do I mean by that? The language is that we know that this number is in base 10. What does that mean? That means that the 7 corresponds to the 100th position, 10 to the power 2. The 2 corresponds to the 10th position, 10 to the power 1. And the 3 corresponds to the 1th position, 10 to the power 0. And I don't have to say 723 base 10. It's assumed, right? We all work in base 10, unlike languages, metric versus non-metric. There are many other conversions that we always have to worry about. So when I say a temperature, Fahrenheit or Celsius, when I say a distance, kilometers or meters. But one of the nice things about numbers is that we've agreed on a base 10, okay? And that's the language of numbers. And it's implicit, but really there is a rationale behind this number, which is that this is 7 times 100 plus 2 times 10 plus 3 times 1. And I'm going to, because this is how we're going to be doing things in base 10, is remind you that the 100th place, the 10th place, and the 1th place are just successive powers of power of 10. So 10 to the 0, 1, 10 to the 1, 10, 10 to the 2, 100, and obviously 10 to the 3, 1000, and so on and so forth. And that's what we mean by base 10, is that this base is being raised to an exponent, and that forms the base, and then we multiply by whatever number is in that position. So, for example, if I had the number 5,349, that would correspond to 5 times 10 to the 3 plus 3 times 10 to the 2, 4 times 10 to the 1, and 9 times 10 to the 0. And again, when I give you this number, I don't have to tell you base 10. It's agreed upon. We've sort of pre-agreed on this. But we should agree that it's sort of arbitrary. Why base 10? Well, you know, some people think it's because of this. Hey, that's a pretty good fit, actually. Base 10, because this is how we count on our fingers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? But there are, if you look through history, other civilizations that had used different numbers. My favorite example of this is my father. My father, when he counts, he does 1, 2, 3, 4, 5, 6, 7, 8, counting with the thumb. I don't know what he does when he gets to 9 and 10. He can only count up to 8. Base 8 is a perfectly fine number, right? So what does it mean for 257 to be represented in base 8? It means that the base is now not 10. There it is right there and right there. It's 8. So this 2 corresponds to 2 times 8 to the power 2. This 5 corresponds to the base 8 to the power 1 and 8 to the power 2. So notice that this number, and this number are exactly the same, except I've simply replaced, in the previous example, 10 with 8, and then of course the exponents work out. And so 257 base 8 can be converted to base 10 by simply working through this arithmetic, and that's 175. So you could imagine a world where some societies work in base 8 and some work in base 10, and we'd have to convert units the same way we convert temperature, distance, weights between metric and non-metric. It'd be annoying, but we could do it. And there's nothing fundamentally wrong with this base, and there's nothing fundamentally right about this base. You can represent all the numbers, they just have a different meaning. Now, base 2 is a perfectly valid base as well. Notice, by the way, that numbers in base 2 only have 2 numbers, 0, 1. So numbers in base 10 have 10 numbers, 0, 1, 2, up till 9. Numbers in base 7 only have 8 numbers, 0 to 7. And numbers in base 2 only have 2 numbers, 0 and 1. Okay? So if I give you the number 0, 1, 1, 0, and I ask you what is that in, say, base 10, well then we play the same game. This leading 0 is multiplied by 2 to the power 3. This one is multiplied, which of course is that one right there, times 2 to the 2, 2 to the 1, 2 to the 0. Work out those powers of 2, so it's 8, 4, 2, 1. Those two are multiplied by 0, so they go away. The 1 and the 4 are multiplied by 1. 4 plus 2 is 6, so that's base 10. Nothing right or wrong about base 2. I can represent any number that I can represent in base 10, which I can represent in base 8 or base 4 or base 16 for that matter. Okay? So the bases are arbitrary. That's the point here. They are arbitrary. We can represent all the numbers. They just have a different representation. That's all. And the reason of I'm doing this is because modern computers talk in binary numbers. They have 2 numbers that they can represent, 0 and 1. And I'm going to talk a little bit about why that is, and then we're going to see how we get from that language of modern day computers to actual computations on binary numbers. But of course we have to understand the language before we understand what's actually being done on that language. All right, so for example, because computers have finite memory and finite precision, we always have to specify how many bits we will be talking about in our binary number. So unlike base 10, I can just give you a number, right? 5,371, 27, 8. I don't have to say this is a 4-bit or a 5-bit or a 1-bit. But in binary numbers, because everything has to have the same length representation, we're going to always specify how many bits are available to us. And simply by bits, I mean how many powers of 2 do I have? So a 2-bit binary number says that you can have a bit in the first position, 2 to the power 0, and you can have a bit in the second position, 2 to the power 1, and that's it. Okay. Now, with a 2-bit binary numbers, you can walk through and figure out how many possible numbers can I represent if I only have 2 bits. Well, I can represent 0, 0, 0. I can represent 1, 0, 1, 2, 1, 0, and 3, 1, 1, and that's it. There's no other bits. So now when I restrict the number of bits in my binary numbers, now I do have a restriction. I can only represent numbers between 0 and 3. That's true of base 10 too. I could have said you have no more than 2 decimal places or 2 positions, then you can only represent numbers between 0 and 99. And there is no 100. So the same thing holds true. I'm just going to now start fixing the bits, and you'll see in a little bit why that is. So let's just make sure we understand this. So why is this 0? Because this number in base 10 is 0 times 2 to the 0 plus 0 times 2 to the 1, 0. What's this number? 1 times 2 to the 0, that's 1. 0 times 2 to the 1, so that's 0. So that's the 1. Okay, 0 there, and then the 1 times 2, that's that. And then, of course, I have 2 plus 1 is 3. And notice that with a 2-bit binary number, I will always, if they're always positive, we'll get to negative numbers in a little bit, I can always go from 0 to 2 to the power 2 minus 1. So in this case, that's 4, 2 to the 2 minus 1 is 3. Okay? So if I give you a 3-bit binary number, my maximum value is 2 to the power 3. That's 8. By the way, if you're going to be a computer scientist, you have to get really good at powers of 2. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 10, 24. You can stop there. 2048 is after that. That one's easy too. Okay, so maximum power of 2 is, largest number is 2 to the power 3. That's 8 minus 1. By the way, why the minus 1? Because I'm starting to count at 0. So notice I have 3-bit binary number. starting from the right, this is the 2 to the 0 position, 2 to the 1 position, 2 to the 2 position. Okay? And you should be able to convince yourself that you can get every number here by doing the conversion I just did. So let's do, say, 5 here. So how do I know that this is 5? This is 2 to the 0. What's that? 1. That's a 0, so I don't care. This is 2 to the 2. That's 4. 4 plus 1 is 5. Go through each one of these, please, at least in your head, and convince yourself that you get these numbers here. Okay, so that's a 3-bit binary number. I can count between 0 and 7. 4-bit binary number, same game. 2 to the 4 is 16. 16 minus 1 is 15. That's the maximum number. We have all 4s there. Minimum number is all 0s, of course. So again, 2 to the 0, 2 to the 1, 2 to the 3, 2 to the 4. So let's look, for example, at this number right here, 11. Why is that 11? Well, let's go from this side. So this is 2 to the 4. What's 2 to the 4? It's 8 plus 2 to the 2. That is, 2 to the 1. That's 2. That's 10. And 2 to the 0 is 1. That gives me 11. And again, pick a couple of numbers here and convince yourself that these are the decimal base 10 numbers correspond to these 4-bit binary numbers. Okay. Now the question you want to ask is, why am I doing this? Is it fundamental to computers? Or is it that there's a reason for it? And it is not fundamental to computers, but there's a really good reason for it, which is that representing binary numbers in a computer is incredibly reliable. And let me tell you what I mean by that. So information, of course, on a computer is stored in terms of electrons. Right? That's how computers are powered. And so we have to be able to represent different numbers. So imagine I want to represent, say, base 10. Let's say I wanted my modern computer to be base 10, which means I have to represent the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? And let's say that the way I'm going to represent, let me do an analog to how the electrons work, is I have a little test tube, and I'm going to fill that test tube with water to the level that corresponds to the number, and then that test tube will correspond or represent that number. So here's a 0, it filled up to level 0. Here's a 4, it fills to 4, 6, and 7. Okay? Nothing wrong with that, perfectly fine. But what if that water level was a little unstable? What if it was shaking around and it was moving around a little bit, and that means a 0 might accidentally look like a 1 every once in a while, and a 7 may accidentally look like a 6 or an 8 because of a little bit of instability. Now obviously this is not water in a modern computer, but these are electrons. Electrons have a little bit of instability. It's difficult to keep that level at exactly the right level, and so to distinguish between 10 distinct levels is just not very reliable in a computer. And what is reliable is distinguishing only between two things. So here's my test tube again with water in it. If it's empty, it's a 0. If it's full, it's a 1. And now you can imagine if there's a little slop here, this goes down to 8 and this goes up to 1 and it slops around, I can still distinguish between those. So we want representations that are incredibly distinct from each other. And when you have to do 10 levels, you have to have a much finer resolution, if you will. And if you only have 2 levels, it's actually easier to deal with fluctuations in the internal physical representation. And that's, in a nutshell, why we use binary numbers. Okay, good. So what have we done at this point? We've said that binary numbers are the language of modern computers. Now, it's not entirely clear what I mean by that still. What do I mean by language, right? So when it comes to numbers, sure, I'm going to use base 2 instead of base 10. But what about letters and strings and other things? We'll get to that in a little bit. So the language of modern computers is we are going to talk in base 2. The reason we're going to talk in base 2 is because of the reliability with only having to store 2 states, 0, 1. Okay? Now, at this point, I've shown you how to represent, using an n-bit binary number, numbers between 0 and 2 to the n minus 1. That's the maximum number you can represent. But obviously there's other things I'd like to represent. What about negative numbers? What about floating point numbers? What about strings? So what we're going to do when we pick it up after this lecture is we're going to start talking about how to do things like negative numbers, and then we'll talk about fractions. And then once we understand the language of modern computers, binary numbers, we're going to talk about the nature of computation. How do computers actually compute on these binary representations? All right, that's it for now. We'll pick it up in a few minutes. See you soon.